Okay. Good morning. This is Guoliang Ma from Fudan, Shanghai. I'm very happy to give this talk. And I first thank the organizer for giving me the opportunities. And today I will talk about the nuclear structure input and CME as the organizer request. And our work is based on these two papers, one recent paper and the other is a new paper. I just post on archive this week. Here is the outline of my talk. First, I'll give a short introduction. Then I will tell you how to set up a model. And next, I will show two examples. First is the nuclear structure and the CME isobar clearance. And the second one, I will re-examine two-plan method. Finally, it's a summary outlook. So let's start with the QCD vacuum. We know the QCD vacuum. That it's actually the vacuum is not a real vacuum. There are lots of fluctuations. The top loop charge fluctuates in the QCD vacuum. And so due to the fluctuations, it can produce the chiral imbalance. So with the balance, we can have the local parity of the charge and parity violation in the strong interactions. So this is a very fundamental questions, important questions. So to study this, the QCD vacuum, to looking for the QCD vacuum fluctuations. So we need to find some possible ways to look for this kind of QCD vacuum fluctuations. So one possible way is through the chiral magnetic effect. With the strong magnetic field, with the hyper of strong magnetic field, which can produce by the high ion clearance in the early stage, and coupled with the chiral imbalance, it can make electric charge current. So it means we can have charge separation. So how to observe the charge separation experimentally? So the first experimental observable was proposed by Professor Lawson in 2004, and by using this charge and mutual correlation, by using these correlations, people believed it can reflect the CME effect. So in this term, the PA1 term, because the background term can be largely cancelled out, and the directed flow term is negligible. So this is the first star result, and the result is consistent with the dipole charge separations, the opposite charge, the same charge correlations. So as expected by the CME, and the news was released in the 2010. Announced the result.
Can I ask a question?
Yes, please.
I didn't understand. What is the difference between B in and B out? You probably said it, but I missed it.
Okay. So the in and out means the in plan and out plan. So it means the in the reaction plan and the out reaction plan.
Okay,
So okay.
thank you.
Because it's the minor sign and these two background terms can be cancelled out largely. This is the argument. Okay. And this the results indeed show these charge separations. So it's consistent with the charge separations. So the news announced a hint, the bubble broken symmetry in the quark loop and rig. So this is the old news. However, the things always complicated. So the background and signal always come together. So if there is signal, there always a background. So in order to observe the signals, we have to understand the background. So for the CME, there are lots of background sources, so like the electric flow, resonance, and the local charge conservations. So after 10 years hard experimental hard research, and recent the star results indicate the CME fraction inside the dirt gum observables is very small. Background is dominant. So the next questions. So is there a good way to reduce the influence of the background to find the CME signal? So the isobar clearance was thought as a promising way to search for the CME. The ruthenium, zirconium, they have the same mass but different charge. So same mass, because same mass, we expect they have the same background, but the different charge. So the ruthenium has more charge. We expect the ruthenium has a larger CME signals than the zirconium with less charge. So in our work, we predicted 400 million events at 2/3 background levels. The relative difference between two isobar clearance can reach 5% with 5 sigma significance. So in the 2018, STAR actually collected more data, 1.8 billion ruthenium and 2 billion zirconium. Look for the CME expectations. The CME expectation expect the observable ratio, the ruthenium over zirconium, larger than 1. And the 5 teams conducted the blend analysis. So this is the first isobar results published in the last year, and the 5 experimental analysis group agree that the ratio, there are lots of different observable ratios. All the ratios are generally less than 1, and no obvious the CME signal is found. So this it's not good news, but we have to understand how to understand these results. So let's first understand the background. Actually, if we compare ruthenium, zirconium, we find the difference. The difference in the multiplicity distributions, the difference in the number of charge as function of centrality, and the difference in the V2. So in order to describe the experimental data, so the star paper actually they apply three deformation cases, and they found the case 3 can describe the experimental data. So it's possible there are lots of other cases. This is only 3 cases. So actually this relate to this the central topic of our program, relate to the nuclear deformation and structure. So there are lots of works, so including Jiang Yong and Chun Jian work and many gentlemen. They gave consistent results. They found for the different observables, and all the ratios are between the ruthenium and zirconium are sensitive to the deformation, nuclear deformation and structures. So when the guard closes the door, he opens a window. So, but I want to ask, is the door closed tight? So our focus is still on the CME. So let's look at the status of the CME. This is the results from the star. This is using the 2-plan method. Let me explain what is the 2-plan method. This method is proposed by the Hao Jiexu, the next speaker, and the Professor Fuqiang Wang. And they use the 2 plans. The one is the reaction plan, which can be measured by the spectral plan, and the other is participant plan. And use these 2 plans as a filter. To filter what? To filter CME and background. Why? So because the 2 plan has different correlations with background and CME. For example, for the reaction plan, so if the signal, if relative the if we measure the observable relative to the react plan, and we can get the CME entirely, but the background will times A is a factor usually smaller than 1. It means the after the filter and the weaken, the background is weakened by a factor A. So on the other case, for the participant plan.
So there's a question. There's a question.
Okay.
Since this is important for the rest, can you explain? I understand one plane, which is the spectator plane. How is the other plane determined?
Okay. So the other is participant plan. Participant plan can be measured by all the charged particles experimentally, and by look at the geometry, I mean the momentum anisotropy, and we can determine.
That is participant plane, yes?
Yes.
Participant plane is elliptic flow determined from particles in the central gravity region.
Whatever comes out, that's your plane.
Yeah, and the spectator,
Okay.
it's also a V1 plane. It's
okay.
It's the first harmonic.
Okay.
So it's not the same particles and not the same harmonic.
Okay, thank you.
Thank you for the hype. Yeah, for the participant plan, they are more sensitive to the background, the flow, electric flow. So if we measure the signal relative to the participant plan, we can have the background entirely, the whole background, and the CME will be reduced by a factor A. So then we can, if we assume, we can assume the total signal, the total observable has two components. The one is background, the other is the CME. So, and we can have the two signals, and the two signals can decompose the two parts. Okay, so then we have a system of the two equations, and we can solve the equation. We can get this F is defined as the dirt gum CME participant plan over the dirt gum participant plan. So it means the how much the fraction, the CME signal inside the total the observables, the fraction. Then the fraction can be determined by the two A, capital A and small a. And this two A's are two ratios. The capital A is the dirt gum ratios, and the small a is the V2 ratios. So these two ratios can be measured experimentally. And once we measure these two ratios, we can calculate by using this equation, get the fraction CME. This is the results from the star experiment. The left finger shows in the isobar date, the FCME are consistent with 0 in the isobar clearance. And the right hand, the finger show the FCME in the GOGO data, so 200 GeV. And the data show limited CME signals, the right symbols, but with less significance. This is the two-plan method, which used experimentally. However, I will argue there may be a problem in this experimental method. So in this method, they assume this on the left-hand side is experimental way. And in this experimental way, they assume the CME and background after they have same transmission rate, the transmittancy. So, but if we don't see, if this the two the CME and background have different transmittance, then we can have the right hand side. So we can see, so this the difference. I just the circle with the red and blue, and we can see if we the final result. This is the final result. If A equals B, this one will be reduced to this one, the experimental one. But the question is whether the CME transmittancy is same as the background transmittancy. So in principle, the CME and background, they are two different things. They should have the different transmittancy. So, however, the CME transmittancy is not experimentally measurable. Experimentally, we don't know the CME. What is the CME in the signal? How much in the signal, in the observable? But this can be calculated by a theoretical models. Next, I will use the AMPT model. This can easily obtained by the AMPT models, because we know the CME, the the CME part, the CME component into the signals, which can be just by calculate by this, the with CME, the dirt gum from with CME minus the dirt gum without CME, measure the difference. This can be assessed by the model of IMPT models. So because the CME signal, I will show you it depends on both initial and the final state. So in this way, the B actually is time dependent. So, and I will show you actually the B is not equal to A. They are different later. So why I choose the IMPT model to study the CME? We know the CME, the generation of the CME rely on the magnetic field. However, the magnetic field is quickly decayed. So in this way, the CME effect is an initial effect. However, the high-ion clearance include the final state interaction, lots of different final stages. So the questions, can the initial CME effect survive the final state interaction effect, so in the high-ion clearance? So until to the observe, the final observable. This the interest, our interest questions. So to understand this question, we choose the IMPT models, which invited by the Zwilling and also Ziming Ke and Baoan Li, who is in the audience. And these models include the four basic stages, the initial conditions, and the pattern cascade, and the hadronizations using the quark coalescence, and the hadron reschedulings, the hadron cast evolutions. So, however, in order to study the CME, we need to introduce the CME dipole charge separation. And we introduce this charge separation into the initial conditions before the QGP evolutions, since it's an early effect. So the CME can be introduced by a percentage. The percentage can be defined using these formulas. And the meaning is we switch the F% downward moving U quarks with those up moving U bar quarks, and like for the D bar and D quarks. So basically, I switch the momentum for fractional quarks and make the charge separations. And we put a signal, the CME signal, into the initial stage and study the final effect on the imported the signals, including the pattern cascade, hadronization, and random decay. And I should claim the electric field. I assume it's already vanished in the simulations. This is the our first result published in 2011 with Professor Bin Zhang. And what we found is three things. This is our results compared with the experiment date. This is the date shown by the band. We have 4 kind results. The 0% means the without CME signals, and the 5%, 7%, 10%, we increase the CME strands. And we can see for the without the 0%, actually they already have this negative correlations. It's about half magnitude of the experimental results. So, however, we found if we want to describe the experimental data, we have to introduce like 10% CME to describe the go-go data. And if we introduce only 5%, we found almost same with 0%. And 7% is not enough. 10% is good. This is this show the CME observable actually has a nonlinear sensitivity to the CME strength. And the gamma actually cannot respond to the CME strength if the strength less than 5%. And why? We can see the right finger, or please see the right finger. And if we put the initially, we have 10% charge separation, the signal. And after the pattern cascade, it go to this one. This the percentage as function centrality. We can see it largely reduced. And the hybridizations will be increased a little, but the hadron rescheduling, the decay, the resonance decay is decreased again. So from the initial 10% input, finally we can only get like 1 to 2% at the end. Let's try to understand this picture using a cartoon. So on the left finger, on the left hand, I show the without the 0 minibar, the pattern cascade is turn out. And we can see if the without the pattern cascade, without the QGP evolutions, the CME particles, the red one and the blue one are separated. The signal will be resisted to the end. However, if we turn on the pattern cascade, turn on the QGP evolutions, we can see after like 15 Fermi over C, and there actually we can see the signal will be largely reduced. So I just I think there is a very good Chinese poem to describe the fate of the CME particles. I share this with you. I will not read this. So this is the final state effect on the CME signals. And the next I will using the MPD model with the CME signal to study the isobar clearance. So to study the isobar clearance, we have to take care of the two things. The first one is how to initialize the isobar clearance, isobar nucleus. This actually relate to the spatial distribution of the nucleon. Here I list the wooden Saxon form, the deformed nuclear structures. We have 18 cases. Different. We found this the sightings on the market, and so we will put this kind of all the kind of isobars, the deformation cases into the initial condition, into the initial condition part, and run the IMPT with the CME signals, and to look at which one can describe data, which one is better or worse. And we have the three judging criteria. The first one is the multiplicity distribution ratio. The second one is the mean number of charge ratios as function of centrality. The third one is V2 ratio as function of centralities. And we actually, due to the time limit, I will not show all the cases. And we compare all the case by look at the chi-square and look at all the three judging the standard, and we found this the high-low type, so called the Chappie. This also proposed by the next speaker, the Hao Jie. And next I will use this the high-low type initialization. It means the zirconium has a larger the radius for the neutron. So next, this the initialize the isobar, the nuclei, and also we use same technique to introduce the CME signals, and we take care the different charge between ruthenium and zirconium, and we ask the CME current parallel to the magnetic field, event by event. This is the results to compare the star date, the delta gamma as function of centralities. The data are shown by this this one, and we have different CME strengths without CME, and CME strengths increase up to the 10%. So if we look at this centrality, this range, so compare the date, so since the 10% and the 7.5% is overestimate data, and for the other case, they basically can describe data, but for the 2% and the 5%, they look consistent with 0%. And if we look at the ratio of between ruthenium over zirconium, and compare the date shown by the star symbols, and this the overestimate for the 10% and the 7%. For the other case, they both can describe data. So it means the CME actually the strength is very small, even 0 for the isobar collisions for our simulations. And this actually consistent with the latest data from the Jinfeng from the AVFD simulations. They gave the fraction like these numbers. So let's look at the final state effect in isobar collisions. So this picture show if we have initially we have like the 10%, around 10%, and finally the signals will be largely reduced by the final state interactions. It's only have this like 3%. And if we compare the ratio, the fraction ratio between the two isobars, ruthenium over zirconium, we can see for the initial by this shown by the two curves. Actually, they are consistent with the final results. This is shown by the simples. So it means the isobar difference in the CME can be preserved up to the final state. But why we can't observe? Because the signal is too small to be observed due to the above described nonlinear sensitivities. So the next question, is there a good way to extract the CME signal? So then we come to the second part, the two-plot method, compare A and B. This is our new work. So we focus on the two transmit rate, the transmittance, the background transmittance, and the CME transmittance, denoted by the A and B respectively. We asked the two transmitters are same or different. This is the results. And we found for the A shown by this open simples for the different percentage, for the different CME strengths. Here we use the P denote the strengths in order to contradict with F, use or avoid the same letter. This here but the B we can see is basically all the below the A. It means the B is smaller than A for either ruthenium and zirconium. Okay, so if we take the ratio B over A, we found the B over A is about half. So it means the B is like half of A in the isobar clearance in this centrality region, like in the 20 to 50%, which is the most interesting region for the CME. So what's the impact of the B on the CME? So here I show the two kind of FCME. The first one is experimental defined FCME. The second one is the FCME with the B, with considering the B. So, and we found for the first FCME shown by the open simples, they are larger than the solid simples, the FCME with B. So if we take the ratios, the CME B over FCME, and we found these ratios are basically below 1. So next question, I will ask we have two FCME, which one is closer to the real, to the truth, to the real one. So so to know this, we define the true CME, the real CME, the third FCME. So here it can be assessed by in the model, because we can calculate by in this way. the delta gamma without CME minus delta gamma with with CME minus the delta gamma without CME and divide by the delta gamma with CME. So this shown by the blue color in the blue color, and for the first one, experiment one shown in the black, and the second one with consider B in red. So if let's focus on this solid one, we can see the red one is more close to the blue one than the black. For the open, it's safe. So it means if we consider the B, the FCME B will be closer to the real value FCME P than the FCME without B. So
this is by definition, right? Because since you can measure this, you can measure the B in the model. That's the true value. So therefore, by definition, you will get improvement. Because you know you actually calculate
yes.
the value, which is the B, which is not the same as A. Therefore, in this model, by construction, that should be the correct one. And so your red and blue should be always the same, you know, apart from the statistical fluctuation, because by definition, the 2 and the 3 are the same thing, right?
The definition shown here.
What I mean is the way the arithmetics, this formula should give you is equivalent to the 3, right? By definition, because you define everything based on the model. So whatever model gives you is the truth in this model. So I'm just saying the fact that 2 and 3 is a property. I mean, it's by definition in the model. Right?
The second one is more close to the truth. Because so
it's definite. It's by construction. It must be the same.
Because the B is calculated by the third method, right?
Yeah.
The B, your B, right?
B define as let me show the definition. The B.
Yeah, basically, B is calculated from the blue points, right?
Yeah, the B is actually defined here.
Right.
Yes. This is only can calculate by the model.
Right, yes. And the way to calculate B is using the blue points, right? Using the blue points on your last slide. Effectively, right? Because
the next. B is actually calculated by this one, this formula. Okay.
Right, which is your blue points, right? Which is on the
24, slide 24.
Yeah, which are the blue points, right? Because that's how you calculate B. So by definition, these two should be the same.
The blue points is F. It's not B.
Yeah, but you know, to some limit, they must be almost the same, because you use the model, the true CME signal to define your B, and then you also use the true CME signal to define your blue symbol. So there's some, yeah.
Okay.
So we are a little bit running over time, but maybe we finish and then ask a few questions.
Yeah, maybe I can ask another question here. So the third one, right? So you take the signal to be P on equal to 0 minus P equals to 0. P equals to 0 meaning that you did not introduce the CME signal. But once you introduce the CME signal, your part on phase space distributions are going to be different, and now the subsequent evolution is going to be different. So the question would be that, whether the P equals to 0 is the real background for your CME signal, for your CME events. And that's
we check
But
the for
if you
the
treat,
V2
yeah. But in my
the
opinion,
little
if
change.
the additional signal is a perturbation to first order should be.
yeah, well, yeah. First of
Because
all,
everything is a small perturbation.
right, but we're talking about small thing here, right? You extract. a
Yes,
very
we
small
we check the as there's a little effect on the V2, but yeah, I'm not sure how little we should care. Okay.
No, it's unclear to me that the background should be P equal to 0. Right?
Because the change we in our way we only switch the momentum.
Right.
The total momentum is conserved.
Right.
Yeah, and it's a small fraction change.
It's possible, yeah, but yeah. So first order, it's a good approximation, but it's not a guarantee.
Okay.
Because you switch quark and anti-quark, right? You switch quark and anti-quark momentum. And once you do that, your later evolution is going to be different.
Yes, but we take the average. We always take the average. Average it can be cancer. The change the change can be cancer. Could be cancer. If we
Okay,
take average.
We go to the last slide and
Okay, we almost the last one. So I will argue the current experimental way may overestimate the FCME. So this is the last one. Because so let's try to we try to understand why A and B are different. In this one is an important result. So this is the A and B, the definition. So we see for the A is open one. This open one. We check the A for the different evolution stage, and also for B. For the A, it's almost independent of stage evolutions. But for the B, the initially B is shown in the black, and the with evolution, the after cascade in red, and after coalescence in blue, and the final state in green. We can see the B decrease stage by stage. So it could be due to the decorrelation of the CME relative to the spectator plan and participant plan. And this also can be seen by the ratio. If we take the B over A, we can see its decrease with evolutions. So the A and B are we don't check the go-go clearance. This is the guess. The A and B are more different in the go-go clearance. So due to the more strong interaction in the go-go clearance than the isobar clearance, so can it decrease the current observed finite FCME in go-go clearance? So this is a summary. So with the AMPT plus the AMPT plus CME, we got several messages. The final state interaction greatly reduced the CME signal. We found the nonlinear sensitivity of CME observable to the CME signals. And we confirmed very low strength of the CME signals in isobar clearance. We found the B correction to the two-plan method will lead to a reduction of the CME fraction. And the last, for the outlook, we hope more accuracy search for the CME in higher statistical goal clearance in the future. Thank you for your attention.
Thank you. So are you going to be available? I know it's a stretch for you, but if you're not available for the afternoon, I would suggest we take a few questions.
Very, very hard for them.
And then maybe Brian, if there's a little bit delay because both speaker online, so we can continue the afternoon if you don't mind. Yeah, because otherwise we will not.
I have a question on the last slide, 25, the previous slide. So the quantity A, right, is by definition the final state quantity, right? It's a final state measurement of V2, and I think that's why A does not change with your evolution, because that's always the final state.
Here, actually, we measure the A at a different stage. So, for example, for the after pattern cascade, we measure the V2, 2V2 after pattern cascade and take the ratio. And after coalescence, we measure the V2 after coalescence. We calculate this. We stage by stage calculation.
Okay, but by definition, the V2 ratio is the angle between SP and PP in your model, right? Always.
No, but the PP is defined using the initial state. It's not using final state, right? You have a participant plan using all the participating nucleons, right?
Yes.
When you say weight of PP, are you calculating weight relative to the participant plan, which is defining the initial state?
Yes. The spectral plan is defined by the spectral neutrons in the calculation.
Yeah, that's what I mean, right? So it's SP and PP is determined. It's the same direction for the entire time.
Yeah, but the flow can decorrelate from that. It's not. Doesn't have to be the same.
No, but the flow is. So basically, what you have is that you have a flow vector, and you project onto PP and SP, right? And that's the ratio. So it actually does not depend on your flow vector.
Well, if the final state is cause decorrelation, then they may not be the same.
No. You decorrelate, but the SP and the PP are fixed, and you get a vector, and no matter how you project, right, the difference between two is always going to be the difference between the two planes. The difference is always going to be the open angle.
But the same argument applies for the B parameter also.
I think
because there you also use the true plane.
No, but I think the B. So I think the issue is in the definition what B is, right? We have if you measure, everything is measured in final state, right? In experiment. So basically, in your final state particle distribution, you have a CME vector. Let's put it that way. So you have a CME vector along the SP.
You project.
Yeah, and you project. So by definition, if everything is defined by a final state particle distribution, then A and B should be the same because that's the same angle.
That's the final state in the start, solid and open start. That's the final state. That's his definition. He defines stage by stage by projecting to the SPP and SP. Right,
but that's his P delta gamma. I don't know what his delta gamma is got from the delta gamma of P non-zero minus delta gamma of P0, right? So it's not something that we will do experimentally. Experimentally, you have a final state particle distribution, and then you just do projection. So that way A and B is the same thing, have to be the same. Now, of course, if you project this to the initial state, what the initial state CME is, then William might be right.
No. Sorry, William, let me answer. Your P definition is not the difference between P equal to 10% and P equal to 0%, right? This P is calculated. I understand it's calculated directly according to this formula. Is that true?
Right, but you don't know CME, right? You have to.
This formula, if I write this formula in more detail, so this the numerator will be the dirt CME. This equal to the dirt 10% minus dirt
it's not
0%.
Right. And so that's a model study, of course, and it's valuable, but experimentally, we measure final state particle distribution. And with that, A and B are equivalent. It's the same thing. Now, what you measure is really the CME vector along the SP direction. Now, that may not be the initial CME vector. And that's another question.
I forgot to mention one point. So if we look at the black one, so this is the initial B. The initial B is close to the A, but it's still smaller than A. So this could be the B direction. It's not exactly as the reaction plan as the reaction plan.
Right, it's guaranteed that it's not the same direction, right? Because of fluctuation,
yes,
your magnetic field direction can be quite different. But
yes,
average is along the SP direction. So therefore, event by event, the B vector fluctuates around SP, right? And so the B is fluctuating around the SP, not around the PP. And because of that, then by doing event averaging, it should be just the average ratio. So it should be just the SP over PP ratio. Because, right, your B direction is different from SP, but it's kind of random fluctuation around SP. Right? And therefore it is cosine, so it's cosine twice the B direction divided by cosine twice the flow direction. And the flow direction fluctuates around PP. The B direction fluctuates around SP. So you have reduction of the fluctuation, but on average, it's just SP over PP.
I understand your point. But
Even
we indeed see the stage decrease. It's obvious the effect.
Yeah, I think because that's something different, something that experiments cannot measure at all.
No, but this is using the model to explore the evolution. So
right.
This is very useful.
Right, sure. So that's useful in the sense that you measure experimentally this value, what it means in terms of the initial CME signal, right? That's good.
It's also our motivation. We hope to provide some information about from the theoretical study.
I have just follow up. If somebody ran this in the AVFT, whereas you have hydrodynamics instead of MPT as the background evolution, I don't know. Would you expect to see something similar because they also contain all the final state effect, right?
I would think so.
I think it would be worth to check it.
I think it's because the final state evolution.
I'm not familiar with AVFT. Yes.
So Shuja will be here next week. You can ask him.
AVFT is kind of a hydrodynamic evolution.
Yeah.
And MPT is cascade. And at the end of the day, probably they're very similar. That's my guess.
We should check it because the non-flow is different. For example,
that's true.
all of this. Okay, so
Can I have a comment here?
Yeah.
Okay. So I think there's one way the A is not equal to B, that if the final CME current is not the direction of the original CME, current, which means the evolution change the direction of the CME current. Then in this way, I think B can be not equal to A. If the final CME current is equal to the original CME current, I think B equal to A is a very good approximation.
And I think this is the reason, right? That basically,
Yes.
you
Yeah,
find-
from my cartoon, you can see the CME current destroyed by the pattern cascade by the final.
Yeah. I think maybe that's the way why B is not equal to A.
Maybe these few questions I can write down, and if you're here, we can discuss. With the if the speaker is not around, we can still discuss a little bit.
Yeah,
Okay.
I wanna.
Okay, but then
That's-
then
yeah,
we
that's
skip.
another-
Okay, so I think we should move on to the next talk. Thank you, Guoliang.
Thank you.